Hello all. Today, before we dive straight into today's topic, I want us to take a moment and actually look at these three figures that we have here. Pause the video and I want you to see how you see these growing. So try to answer some of these questions. How do you see the pattern growing? Use colors to actually show where you see new squares being added. And then can we figure out or try to draw figure 4, how many of those squares would be in figure 4 and figure 5. And then we don't want to draw all the ones between 5 and 43, so can we try to figure out a pattern and what that might look like? So please pause this video, try to answer some of those questions. Okay, so you could have seen this totally different, but the way that I kind of saw it was that this row right here and this column was kind of getting added into the middle, and then the one little box on the top and one little box on the bottom just gets kind of added onto that. So the one on the top, the one on the bottom, those two boxes are kind of just our constant, and then again we have a row and then this column that's getting added on there. So in figure 4 I would have another row and another column added. So I think right here in figure 3 there are 17. So there's 17 little boxes right here. So in figure 4 I would be adding on 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd be adding on 9 to that. So in figure 4 I would actually have 26 26 little boxes there. And then you may start to notice a pattern that is actually happening here. So when I was going from figure 2, which had 10 boxes, I added on 1, 2, 3, 4, 5, 6, 7. So I added on plus 7. This one was plus 9. And our next one would actually be a plus 11. I'd be adding on 11 boxes. So in figure 5, I would add now 11 boxes to that, and I would actually have 37 boxes in that. And we could also sketch it out if we wanted to. So kind of thinking about what figure 43 would like, hopefully by now you've started to notice this pattern, that the number of rows that we have is also the number of figures, like the number of figure it is. So in figure 43, I would have 43 different rows right there, and then I would have, it looks like it's 2 more than how many rows we have. So it would be 45 right here, and then I would have those 2 little extra boxes on the top and the bottom. So 43 times 45 plus those 2 little extra boxes, it would be 1,937. So again, rows right here. This would be my height, or sorry, my width. And then those 2 are just our constant that we would have. And I really want to focus on this too, because if I go back to just a figure 0, which doesn't really make much sense, I'd be getting rid of this row right here, and I would actually just have those 2 little constant boxes. So how many little small squares would be in figure 0? Just 2. It would look like this, but probably with those 2 boxes stacked on top of each other. So that's truly what makes this our constant that we would have. Okay, very last question. Can we come up with a rule for how many small squares would be in figure n? So I'm going to follow through with this 43, figure 43, but let's think about this now as figure n. So I would actually have n rows, and then I would have 2 more than that, so n plus 2 as my width, and then I would have those 2 little extra boxes that I started with, so plus 2. And if I actually distribute that out, I have n squared plus 2n plus 2. Either one of these equations would actually work. The last thing that I kind of want to talk about here is that pattern that we saw. So here, if we look at our difference, which this would be called our first difference because it's our difference between our boxes that we'd have, you start to see that there's a pattern there. So we're adding the next odd number to it. If we take a look at our second difference, we'll actually see that our second difference is a constant one. And that is truly how we know that this is going to be quadratic. It's kind of equivalent to if you take your second derivative, you would just end up with 2. So that's kind of like tying all of those things together. Now, why do we start out with this activity? This activity has everything to do with what we're going to be talking about, but it gives us a really good visual representation. So I'm going to introduce some notation. I'm just going to write them as notes in the side. So we can actually write, you've seen sequences before. So sequences, this pattern right here, like 5, 10, 17, 26, 37. And then if I had like another blank right here, that would be a pattern that we're predicting. So I can actually refer to this as a sequence. And the way that I would write that is it's just like function notation. Instead of f of x or anything like that, we usually use an a and then a little subscript n. And this would be our sequence notation, and then we'd give it as a pattern right here. A lot of times you'll also see a sequence written with these brackets, and we'll say n goes from 1 to infinity. So kind of like you've seen it with summations, but this would be for a sequence right here. And there's this little subscript tells us in our diagram what figure we would have. So right here, this would be like a sub 0. This would be our starting value. And so usually our n starts at 1, but if we actually go back to the 0th term, so right here I would be subtracting 3 instead of adding 3 because I'm going backwards. That also tells us what our constant value is going to be. So our 0th term is always our constant term. Other notations, so figure 43 would be a sub 43, and we found out that that was our answer. And then I could do the same thing with those subscripts when it comes to our figure 4, found out there was 26, and our figure 5, which we found out there was 37. So this is our notation, but I wanted you to have a good visual representation of that. So our next little part right here is just some summaries of what a sequence is. So a sub n is a sequence where n is the term number and a sub n is the term value. So we have the first term, the second term, the third term, and we can actually write this a couple different ways. So you're mostly used to it probably as an explicit rule. So in this case it was a sub n is equal to 3n plus 5, but we could also do it as a recursive rule, so that does depend on what the previous term is. And so in our example from up above, I could have written it recursively by saying, hey, my very first number, my very first figure has 5, so this is recursive. My very first figure has 5. And to find the next term that I have, I'm going to take my term from right before, so a sub n equals, and this is my term from right before, a sub n minus 1, previous term. And what I'm going to do is I'm going to add the next odd number that I would have. So odd numbers, I believe, are like 2n plus 1. But let's try that out for just the very first term, or actually second term. So a sub 2 would be equal to the term right before, which we know is 5, plus 2 times our n value, which is 2, plus 1. So I would have 5 plus, and then this would be 4 plus 1. And I believe that actually works out because our next term, our second term right here was 10. So 2n plus 1 is like an odd number. If I just had 2n, that would be an even number. So this is how we can rewrite that pattern recursively. in our next section, but we'll talk a little bit. I wanted to introduce this notation now. We're mostly going to be talking about sequences, but a series is a sum of a sequence. So what I can do is I can actually, this big summation right there, I can actually add together all the terms of my sequence. And I can add it together until n. I could also add an infinite number together, so I would have a little infinity up here. Don't worry about it too much. We will talk about it more in our next section. I do want to look at a few of these problems here. So when we're writing the first 4 terms of our sequence, we want to start with our first term, which means our n value is just 1. So I'm going to have 1 squared plus 2, which is going to be 3. I'm going to have 2 squared, because this is my second term, 2 squared plus 2, so 4 plus 2, that's 6. And you can probably start to see the pattern here. It's a lot of like function notation. So 3 squared is 9, plus 2 is 11, 4 squared is 16, plus 2 is 18. And then over here, we can also do this. This would be called, well, actually, I'll tell you what it's called right after we try this. So a sub 1 means I'm plugging 1 in for n. So I'm going to have negative 1 to the first power, just negative 1 over 1. So negative 1. My second term is going to be negative 1 squared. So I'm going to have something positive over 2. It's going to be 1/2. My a sub 3, maybe you start to see this pattern. Now I'm cubing a negative, so I'm going to have a negative 1 there over 3. So it looks like negative 1, 1/2, negative 1/3, and my fourth term would actually be a positive because I'm cubing, or I'm raising my negative 1 to the 4th power over 4. So we actually call this an alternating sequence. And the reason why it's alternating, it goes from positive to negative to positive to negative, and that's that little negative 1 to the n power. Go ahead and pause the video and try these next few on your own. A good place to start would be looking at the difference between these and seeing if you can figure out a pattern there. So I noticed this pattern of adding 3 each time. So my 7th term, my a sub 7, is going to be 21 because I add 3 to my 6th term right there. And because this has a first common difference of 3, I know that this is going to be linear and my slope is going to be 3. If I think about this as my term, I might have to like subtract or add depending on what our 0th term would be. But if I go backwards, so subtract 3, my 0th term is actually 0. So I don't really even have to write that plus 0 whatsoever. Okay, on this next one, I think this 1 would be like a 5 over 5. And so my 5 is kind of constant right there. And then my term on my bottom is actually growing. So I think my a sub 7 is going to be 5/7. And then let's think about this as a pattern that is changing. So my 5 never changes. My 5 is just chilling right there. And if I'm thinking about my very first term, on the denominator it's 2. My second term on the denominator is 3. So it looks like it's 1 more than what place it is or what figure it is. So it's 1 more than what place or what figure it is. And that would be my equation for that.